In this lecture, we're going to have an example of how our constitutive relations can help us explore the relationship among displacement, stress, strain, and tractions or loads. So we know that displacements are related to strains. We have our strain displacement relations. Now we also know that stress and strain are related to one another, specifically in our case for linear elastic materials. And we know that tractions and stresses are related to one another. And so we can jump into this loop at any point that we want and find out the information on all the others. The goal is to find equations for these items that satisfy equilibrium and compatibility for stress-strain relations. So for this, we're going to illustrate this approach with a very simple example, that of just basic tension. So let me clean off this page and then we'll start with that example. I do want to mention that even though this example is fairly straightforward, it's just to illustrate what we have for our approach, and we'll be able to use this approach for more sophisticated type problems as we go through the rest of our course. And so for our example, I'm going to take sigma to be the stress in the z direction, in the vertical direction in my picture. And then all the other stresses are going to be 0. We'll have an isotropic material and we'll have small deformations. Well, we can write down what our stress-strain relations are. Here's the tensor form of our 3D Hooke's law. This may be a slightly different format than what I have written it before with the Lemay coefficients, but this is our typical E and nu, our Poisson's ratio and our modulus of elasticity type form of these equations. So epsilon ij is equal to minus nu over E sigma kk. It's the trace, that's 3 terms, sigma x plus sigma y plus sigma z added together. Kronecker delta ij plus 1 plus nu over E sigma ij. Alright, well, let's evaluate the trace of the stress tensor in this particular example. In general, if we use coordinate stresses, we'd have sigma x plus sigma y plus sigma z, and in this case, since those first two are 0, we're left with sigma. So we can calculate our strain in the 1-1 direction. Okay, and that's like the x direction. So let's see, if that's the z direction, I think I'm going to have like x over here and y over here for a right-handed coordinate system. So epsilon 1-1 would be equal to minus nu over E sigma kk, which is sigma. Kronecker delta ij, Kronecker delta 1-1 in this case, that's equal to 1. Then we're going to have plus 1 plus nu over E sigma ij. Now sigma 1-1 is equal to 0. So what we're left with is minus nu sigma over E, which is what we expect from our regular Hooke's law, as you might write it in undergraduate mechanics materials. If If we do the math, this is the same as epsilon 2,2. Now, epsilon 3,3, the strain in the z direction, is going to be minus nu over E times sigma kk, which is sigma, times Kronecker delta 3,3, which is equal to 1. And then we're going to have a plus 1 plus nu over E times sigma. And if we reduce this algebra down, this works out to be sigma over E, which is exactly what we expect. Now, we said we were looking at small deformations, so we have our strain displacement relations that we can write down. Epsilon ij is equal to 1/2 ui comma j plus uj comma I, or we were to expand this out with instead of using the comma for the partial derivative, we can write it as partial of u sub I with respect to x sub j plus the partial of u sub j with respect to x sub I. So the strain epsilon 1,1 is going to be equal to 1/2 partial of u1 with respect to x1 plus the partial of u1 with respect to x1. There's two of those, so this reduces down to partial of u1 with respect to x1. Likewise, strain in the 2,2 direction is the partial of u2 with respect to x2, and the strain in the 3,3 direction is the partial of u3 with respect to x3. Now what we're going to do is we're going to integrate this system of equations. We know what the strains are now in terms of the stress, so we're going to integrate those equations. Let me make a little bit of room and we'll go through that process. Alright, so let's take a look at our first one. We have the partial of u1 with respect to x1. It's going to be equal to minus nu sigma over E. We're going to integrate a partial derivative. If we get u1 on the left-hand side, we're going to get minus nu sigma over E times x1. But since it's a partial derivative that we're integrating, we could have a function of y and or z as part of this, and we could also get a constant of integration. Now, since we're going to be doing this a few times, I'm going to label these functions f1 and c1, constant 1, for our arbitrary function and constant. Our next one, we can do the same thing. We can have the partial derivative of u2 with respect to x2 minus nu sigma over E again. u2, we're integrating that with respect to x2. It's going to be a minus nu sigma over E x2, but then we could have an arbitrary function of, well, this one would have been x2 and x3 if I'm using this notation. We could have an arbitrary function f2 of, let's see, instead of y and z we're integrating with respect to y, it would be a function of x and z, so that would be x1 and x3 plus a constant of integration, a different constant of integration. In fact, this is going to get kind of confusing for me if I keep this format. Let me first write everything in terms of x1s and x2s, and then I'll go back and put it in terms of coordinate strains. Alright, well, let me go ahead and write down this next one in terms of x1, x2, and x3, and then I'm going to convert everything into x, y, and z. I think it'll be a little easier for me at that point. So we have the partial of u3 with respect to x3. Now this one is equal to sigma over E. And so when we integrate that, we're going to have u3 is going to be sigma over e times x3. And here we could have a third arbitrary function of 1 and 2. Plus potentially another constant of integration. So let me just rewrite these real fast. And this one was x and y. Alright. Well, we do have these arbitrary functions, and this one should be in F2. We do have these arbitrary functions here. We need to figure out what those might be. Now, with some experience, whenever you come into a situation like this, you'll find that you probably want to invoke the shear terms next. So what do I mean by that? The tensor shearing strain epsilon 1, 2 is going to be equal to 1/2 the partial derivative of u1 with respect to x2 plus the partial derivative of u2 with respect to x1. Now in terms of x, y, and z, this is going to be partial derivative of u1 with respect to y plus the partial derivative of u2 with respect to x. Again, I'm kind of mixing that notation a little bit, but I think you understand what I'm doing here. Now there is zero shearing strain in this coordinate system for an isotropic material, so we know that's going to be equal to 0. And so if we get rid of the half, we're going to want to find the partial of u1 with respect to y. Right, so now I'm going to take a look at this second equation, look at the first equation here, and take a partial derivative of that with respect to y. I'm going to have 0 contribution from the term with the x in it. I'm going to get no contribution from the constant, but here I could have a partial derivative of f1, which is a function of y and z with respect to y. And then my second term is going to be the partial derivative of u2 with respect to x. Now look at the second line here, partial derivative of y. The y term with respect to x is 0. The constant term is 0, and then I'm going to have a partial derivative of f2, which is a function of x and z with respect to x. Now the equation I just wrote down with the shearing strain equal to 0 will mean that partial derivative of u1 with respect to y is equal minus the partial derivative of u2 with respect to x. Alright, so let's look at that in a little bit more detail. So the partial derivative of f1 with respect to y and z, of y and z with respect to y, is equal to the negative of the partial derivative of f2, that's a function of x and z, with respect to x. Alright, let's keep that in mind. and let's take a look at our other sets of partial derivatives. We'll make a little bit more room. Alright, so all of that was from epsilon 1, 2 is equal to 0. Let's go ahead and do the others. So epsilon 1, 3, which is going to be equal to 0, is going to be 1/2 the partial derivative of u1 with respect to x3 plus the partial derivative of u3 with respect to x1, or z and x. We can get rid of the half, and so this says the partial derivative of u1 with respect to x3 is equal to negative partial derivative of u3 with respect to x1. And so if we do those partial derivatives, the first term, partial derivative u1 with respect to z, we get 0, and then we're going to have the partial derivative of f1, which is a function of y and z with respect to z, is equal to negative the partial derivative of, well, u3 with respect to x1. We get 0 from the first term, and we're going to get the partial derivative of f3, which is a function of x and y, with respect to x. Alright, so let me drag that over here. Oops. And this relationship is from epsilon 1, 3 equal to 0. And then we have the relationship epsilon 2, 3, that shearing strain is equal to 0, and it has a similar form, partial of u2 with respect to x3 plus the partial of u3 with respect to x2. Get rid of the 1/2 since it's set equal to 0. This will imply that the partial derivative of u2 with respect to x3 is equal to negative the partial of u3 with respect to x2. And I'm going to go ahead and write that over here, keep it in that spot. So it's the partial derivative then of u2 with respect to x3, 0 contribution from the constant term and the term with the y in it. We have the partial derivative of f2, which is a function of x and z with respect to z is equal to negative the partial derivative of f3, which is a function of x and y, with respect to y. Okay, and that is epsilon 2, 3 is equal to 0. Alright, so I'm going to label these equations, and I'm going to label them like my notes where I have called these A and B, and we can call that one C. Now let's take a look at equation A. Partial derivative of f1, which should be a function of y and z with respect to z, is equal to negative the partial derivative of f3, which is a function of x and y with respect to x. Now notice that at most equation A can only come up in the end to be a function of y. We can have a constant in there. We're actually taking care of our constants separately already, but those arbitrary functions, in order for them to be equal to each other, the most they can be then after we take those partial derivatives is something that's a function of y. And by the same reasoning, if we take a look at equation B, the most that can be is a function of x. That would be for 2 and 3. Alright, now we take a look at equation C. That says the partial derivative of f1 with respect to y will be equal to minus the partial derivative of f2 with respect to x. Now, in the end, we're not going to be able to have anything other than a constant term in there, so which is already taken care of in these constants over here. And with that, if 1 and f2 must be constants, then also f3 must be a constant at most. Now, again, we've already taken care of our constants, so in this case, the way we've written it, it's going to be 0. Now there are a couple other things left that we have to do. So now we have the stress fields. All these are going to 0. We have our strain fields. We have our displacement fields. We really need to check equilibrium and compatibility. Now, compatibility equations are second order in the strains. And at most, since our displacements are first order, our strains are going to be constants, so compatibility equations are satisfied. And we need to check our equilibrium equations. Equilibrium equations are cast in terms of stress. So if we have this relationship among partial derivatives of the stresses, let me see if I can write one of them down. So it would be like a partial derivative of sigma x with respect to x, plus the partial derivative of tau xy with respect to y, plus the partial derivative of tau xz with respect to z, plus some body force term in b sub x, and that would be equal to 0 for equilibrium equations. If we look at these terms for stresses, the only thing that we have that's non-zero is the stress sigma z, and it is not a function of z, it's a constant, and so equilibrium is satisfied. Alright, so this kind of gives us an idea of how all these things work together. As I drew on the first slide, we have our displacements, we can get our strains from that, stress-strain relations, and then through tractions if we need them, or if we're given them, then we can go through here. And this was a very simple example, and sometimes these stresses or tractions or displacements are prescribed on certain regions, certain boundaries. In general, what we have are the boundary value problems of elasticity. subject to our different prescribed conditions, either usually on displacement or traction on specific regions, subjected to compatibility and equilibrium. And in fact, now that we have our stress-strain relations, we can write compatibility equations in terms of stress. We can write equilibrium equations in terms of strain or displacement. And we can formulate our boundary value problems in a lot of different ways. And so we'll investigate some of those as we go through the remainder of our course. One of the next things we're going to do is we're going to come up with something called the Beltrami-Mitchell equations, which will kind of give us a more compact representation of this particular boundary value problem. Compact in the end, it's going to take a little bit of work to get through it. So to combine all these ideas that we have together at this point. Now, from a classical solution perspective, it's probably very unlikely that anybody's going to come up with too many more new solutions to closed form boundary value problems of elasticity. So what we're going to do is we're going to go through some classic solutions, and then we'll have an understanding of why finite element analysis is often very useful in elasticity type problems. It'll lay the foundation for you to study that class then as well. And but you never know, you may be able to formulate some new problem that hasn't been solved before in the last 200 years for elasticity.